We are an EU project called SYMPHONY. We are 13 partners from 4 different countries. I think it's very interesting that we have achieved to have 3 large chemical companies, Semperit, Arkema, Piezo-Tech Arkema from France, and Evonik, working together on material development, all working in the field of polymers, and also together with some research institutes, Fraunhofer IC, RISE, Joanneum Research, PCCL, which are all very active in printing and making inks out of these polymers. Also, recently we had a partner change from Evonik to Innovation Lab, so we also have their competences now in printing and processes on board in the project. But we can't do everything by printing, so we also have Virtual Electronic and Infineon developing dedicated electronics for power conversion and chips. And then we have our use case partners, Tubolito, which is a tube company from Vienna, to include pressure sensing. And we have Airlogics developing sensors for wind turbine condition monitoring, where we want to use this for condition monitoring on wind turbines, and Parador, a flooring company, supporting the project in the area of smart floor for detection of room occupancy. So what is the nanogenerators we'd like to develop? On the one hand, we use VDF-TrFE as a main material for energy conversion. So we want to make composites of piezoelectric materials and embed the piezoelectrics in rubber to make it even more soft, to be more compliant to some mechanical problems. We have magnetic particles integrated in the VDF-TrFE, and we also work on structuring to get the material to the resonant frequency. But generating the energy is not everything in energy harvesting. We also need to convert the energy. So in that sense, we have also then flexible rectifiers, because we have a flexible nanogenerator. We wanted to have this also flexible with a printed or solution process technology, rectifiers based on silicon particles embedded in a nanofiber matrix, and also printed batteries from redox polymer batteries, and supercaps based on cellulose nanofibrils. As I said, we want to use large-scale processing techniques like spray coating, screen printing, and roll-to-roll processing, hybrid integration of discrete components. And then I think all the effort only makes sense if we then can apply it in use cases where there is potential to trigger some energy savings and CO2 savings. So on purpose, we selected 3 use cases from energy generation, human living and housing, and urban transport, so bicycles, floors, and wind turbines, which basically are the main contributors to CO2 emissions. So, as stated before, I see a very important point in this field of energy harvesting, that the amount of material, the amount of resources is very high compared to the energy output. So it's very different to solar cells, of course. And the other challenge is this material. So it's the idea that the sensors are in remote areas, that they are distributed somewhere where you want to do condition monitoring. So it's very likely that they are not recycled or deconstructed. So the production of these materials should be cost efficient and resource efficient. So that's why we thought in SYMPHONY that we want to use printing, coating, lamination, and now high temperature sintering processes, for example, for ceramic sintering. We want to use non-toxic materials, so thereby replacing PZT by the polymer PVDF. So PZT is the main running horse in piezoelectric energy harvesting. We want to use polymer batteries instead of lithium-ion based batteries, caps, and final. So to look a little bit into the materials, so our main material is VDF-TrFE, which is a piezo. So in this polymer, in the beta phase, you have a chain, and all dipoles are orientated in the same direction. it spontaneously crystallizes in such a semi-crystalline structure. And if you apply an electric field, you can orient these crystallites in a preferential direction so that you have a macroscopic dipole or so-called spontaneous polarization in the polymer, which is the origin of the piezoelectric effect. And if we look into the piezoelectric effect, we have a spontaneous polarization of around 80 microcoulomb per square meter. At Joanneum Research, we have developed this technology quite for a long time now, screen printing and processing this on different substrates like plastic films, paper, leather, and so on. And if you bend this material, you can see that charges are generated, which can be used for sensing and, of course, also for energy harvesting. What we want to do in SYMPHONY, of course, the PZT is a strong competitor for this material. So D3 is orders of magnitudes higher for PZT. But for energy harvesting, it's important that we have a good electromechanical coupling, so the electric energy related to the mechanical energy. And even if we have like 20 times lower D3 coefficient, which is around 24 picocoulomb per Newton for PVDF-TrFE. PVDF-TrFE has a relatively low permittivity and also a low Young's modulus, which helps in this equation. So we end up a little bit like a factor of 5 to 10 below PZT. But in some applications, we can use the flexibility and the softness of this material to have a better coupling to the mechanical application. And also in the project, we want to work by the composites to further reduce the stiffness and thereby to tune, to bring up the electromechanical coupling. However, energy harvesting is not stopping with the material alone. It takes around 1 minute to change the slide. So it's a multi-scale optimization problem. At first, we have the investigation of the mechanical input. Then, if we have analyzed what is our input, we can design the mechanical transducer to take up this mechanical energy and bring a lot, as much as possible of the deformation in the piezoelectric layer. In the next step, we can design this piezoelectric transducer. This was now too fast. The piezoelectric transducer to basically have, for example, adapting the layer thickness of the piezoelectric material to increase the voltage or to increase the area by stacking a number of layers to increase the current. So this can be adapted according to the electronics we want to power. Then we can work on the harvesting electronics. It's an interesting question. Sometimes maximum power point tracking is valuable, but therefore you need a certain level of energy because if not, the maximum power point tracking eats up more energy than you actually have. Then you have the problem of the energy storage, the size, the time, the losses of the energy storage. And then finally, you most often end up with still too less energy for your application, so you can also work on your application. Maybe you can reduce sampling rate, the frequency of data transmission, and so on. So this is the optimization problem. So as I said, we don't only need nanogenerators basically to do energy harvesting. We also work on rectifiers, and this is a contribution from Sweden, from Rice and Linköping University to the project. So this is a laminated material stack to fabricate a diode with silicon particles in this binder of cellulated nanofibers contacting an aluminium electrode to a carbon electrode, and thereby forming a Schottky diode. And it's possible to laminate this together to form a flexible rectifier with a conversion ratio at least above 50%. On the other hand, we have the supercaps developed by Linköping University and Rice, fabricated by spray coating. And in that sense, this is a very impressive development with a high energy density up to 11 millifarad per square centimeter. So this is a really impressive value, I think, for such a spray-coated supercap based on basically nanocellulose with p.PSS and an electrolyte in between. So now let's quickly come to some of the use cases of the SYMPHONY project. We have the wind turbine, the smart floor, and the bicycle tube. All have different frequencies. So in the wind turbine, we have actuation frequencies about 10 to 200 Hertz. Smart floor, it's more a single event, and in the bicycle tube, we are around 1 to 2 Hertz. Also, the displacement is very different, and also the available area, which is of course very big in the wind turbine use case. And in the bicycle tube, we more or less have the circumference of the tube. So it's a very different problems for optimization. And then if we go into one use case after the other, basically in the wind turbine, of course, we want to do condition monitoring. We want to reduce the still stand times of wind turbines for maintenance and reduction of damages. So we are working together with a company already developing so these patches which can be mounted on the wind turbine, now powered by solar cells, which is good and which should still stay there. But of course, you would also like to have energy when it's dark and in the night to be able to transmit more and more frequently the data, and also to save the amount of batteries which you need to store the energy to bridge this dark time. So this is basically the goals here. And of course, we started with analyzing the it's going very slow. We started with analyzing basically the turbulences and the vibration pattern on the rotor blade. And then there was a big wish of the wind turbine companies that our energy harvester is covered with a thick TPU layer in order to protect it against erosion, which is present on the wind turbine, which is of course affecting a lot the mechanical properties of this situation. We also analyzed by measurement data the vibrations on the wind turbine at different positions from the nacelle, and we could see that we have vibrations in the range of 1 to 10 Hertz with an amplitude of 0.1 G, which is the highest amount. So this is not a huge vibration for energy harvesting, but we started to develop our energy harvesters and first tried it with a closed structure where we could reach, according to simulation and also in experiments, around 1.5 volts open circuit voltage. And we also then checked this in the wind channel, so where we could apply such an energy harvester in the wind channel and measuring the current and the vibration. So we noticed that a closed structure is maybe not the most efficient, so we also went to an open structure and applied an airflow to an open structure. Basically here we could reach 12 volt peak to peak and an average power of 13.8 microwatt by a single structure. Of course, the area is large on the wind turbine, so we can put a lot of them. And basically right now they are on the first time such elements are mounted on the wind turbine, and I'm really curious how durable they are. So if we go to the second use case, the smart floor, you can also look at this in the exhibition hall. We have brought a small demonstrator. So here the idea is that in order to efficiently get the energy into the piezoelectric harvesters, we need some bending. So we designed a structure that we have basically micro cantilevers underneath the floor. We limit ourselves to below 1 millimeter traveling distance, and our goal is to harvest 120 microjoule to have a transmission an RF transmission of the identifier via an ocean board, which is taking 120 microjoule. And we have submitted a publication regarding this, regarding the structure we invented. So the nanogenerator is fully printed, also with some barrier and support structures. Some additional layers are then laser cutted and mounted underneath the floor. And you can run a little bit through this optimization problem, so that there is the length of the cantilever. So with a shorter cantilever, of course, we get more energy per area, but we also need more force. So you have around some 75 kiloperson available on the area of 30 to 50 square centimeters. So we optimized a little bit the layer thickness of the piezoelectric elements and also the cantilever length. And finally, we came up with a design where it should be possible to harvest around 150 microjoule in one step. At a certain point, the slides change. It's really funny. So we came up with a 6-layer design, 3 layers on the top side, 3 layers on the back side of piezoelectric elements, all printed on these micro cantilevers. And here you can see the charges generated by these cantilevers, and basically scaling up to the area of the floor, we end up with 150 microjoule. So I think the time is running quite fast. You can test this at the exhibition hall as a demonstrator if you like. So I don't go into details with this one. And I come to the last use case, which is the bicycle tube. Also there we have brought a demonstrator. So we are working together with Tubolito here. Right now they have a product on the market where they have an NFC harvesting chip inside used for pressure monitoring inside the bicycle tube. Of course, the problem is you have NFC, you need to have the smartphone very close to the tire. So if you want to have a constant update of your tire pressure and temperature during cycling, you need another way. So Bluetooth connection, you need a little bit more energy. That's why we started on bringing in piezoelectric elements inside this tube to do the pressure monitoring. And the idea, of course, is that you have a remote monitoring of the pressure of your bicycle tube, basically during riding, but also, for example, if you think of rental bike stations, they could monitor the tire pressure remotely, thereby having a better maintenance, also improving then urban transport situations. So we started to laminate these elements into the bicycle tube. First we thought we want to do it soft, so that's why we also developed the soft PVDF elements. But then it turned out that mechanically it would be much better to have a stiffer substrate, because then the neutral axis is further away from the piezoelectric harvesters and you have more energy basically in your piezoelectric elements. So this was also then confirmed by some calculations. So that with the soft substrates we get less charges, with the stiffer substrate we get more charges out of that. So we switched to a stiffer substrate inside the tube. And finally it was possible to test this. So we made 2 different designs, 4 layers stacked with a little bit thicker layer thickness, or 5 layers stacked with a lower layer thickness. And you can really nicely see in these experiments how much energy, depending on the speed, on the tire pressure, you can harvest. And also that you can tune basically the output voltage to the maximum power point you'd like to have. So our electronics is powered at 3 volts. So at this, with this system here, we have twice the energy than with this system. So just by changing a little bit the layer thickness and the number of layers, you can really then tune the piezoelectric transducer to what you would like to do. So we have a power output about 350 microwatts in average at the maximum power point. And here also with electronic built an electronic circuit with an improved rectifier, so that we have some MOSFETs here which basically are switched on as soon as there is enough power stored, and we add another 10% of energy transfer and also comparator which can switch on and off the piezoelectric, the pressure measurement and transmit the data via Bluetooth to the bike. So we had a first test on a little bit older system where we really cycled this on the road, and transmission of the pressure data was basically possible every 12 minutes after the first initial charging from 0. Then the cap voltage dropped down again, and we could charge it up again. And yeah, we will further optimize this design. So our goal is to come to every 2 minutes distribution of pressure data. And with this, I come to my conclusions. I think it's very important for this mechanical energy harvesting. So the sun might be the same on Earth everywhere, but the mechanical input energy is really different. So for each use case, you really have to adapt the system, analyze the mechanical input characteristics, how you can transfer the mechanical input into your system. Then, of course, the transducer can be optimized in terms of layer thickness and so on. And then the next step is to optimize the electronics. Right now we are working a lot of multi-layer printing of PNGs, and I think I could show you that really the energy is enough to power some electronics with this. There are a lot of challenges still to be solved, also in terms of integration of all the other components, but we have another 12 months to go in the project, and I think there will be a final set of demonstrators quite soon. So thank you for your attention, and if you want to see more, we have a booth in the exhibition hall, and we can also discuss there more details.
Thank you. Also the difference you made with solar energy and piezoelectronic now here. I'm sure we have scientists here who have questions for you. Who would like to start? Yes.
Thank you, very interesting. Regarding the use cases, have you ever considered biomedical applications? For example, the use of the inner tube of a bike. It reminds me, for example, of blood vessels. So would you be able to, for example, monitor the pressure inside of them?
Yeah, I mean, in this project we are not looking into putting something inside the body. PVDF is used for medical applications, so it could be possible. We have done pulse sensing with PVDF outside, but not self-powered so far. So I think there should be energy available on the body, but I think for this piezoelectric sensing you need quite some motion. So in the elbow there's maybe enough energy, but inside the body I would rather go for biofuel cells, fuel cells or something like that to take the blood sugar for energy harvesting.
Thank you.
Thank you for engaging presentation. I had a question about the rectifying stage. How do you deal with the loss of energy to the rectifiers? Because I saw it's a full bridge rectifier as well.
Yeah. So of course losses are a big problem in the rectification stage. Actually that's where we are struggling also right now, that of course the discrete electronics performs better than our laminated rectifiers. I think it's very important to have low loss rectifier. So just do research and improve it.
More research needed.
Thank you for your presentation. My name is Ngọc Đức Âu. I'm from Lund University. I just asked you a question about how much is your efficiency of your rectifier, because it's very important for your energy harvesting, because high efficiency RF or high efficiency AC to DC rectifier will help you improve the performance of your system. So I just asked you a question, how much efficiency of your rectifier?
Yeah, so Xin Wang is also in the audience developing the rectifier. Maybe she can answer the question if she likes. So right now the conversion efficiency is a little bit about 50%, which is of course not optimum for this application. We strive to improve this a little bit. So for the demos we have in the project, I think we mainly have to use discrete components in that case. But we think of other demo applications where maybe energy losses are not so relevant. We have a little bit of excess energy and we can afford to have a little bit leaky rectifying stage.
Thank you very much, Jonas. I have a personal question
Yeah.
on the tube. You mentioned that you're working on it on hard rather than soft material. Wouldn't that bring a wrong movement into my tire?
Yeah, we thought so. That's why we in the beginning wanted to use soft materials, but actually this thin PT layer doesn't change a lot. So it's not noticeable. We have not tested it with Tour de France cyclists, but yeah. So at this stage, I think it's okay.
Good. I don't see another question, and I think it's also time to move to the next presentation. Jonas, bravo. Thank you very much.